Welcome to this lesson on halogenoalkanes for A-level chemistry. In this topic, we'll learn what halogenoalkanes are, how they react, why their reactivity changes, and how they are used in organic synthesis. Course context and A-level specification focus, structure, general formula and nomenclature, physical properties and trends, bond polarity and reactivity of the C-X bond. In halogenoalkanes, students develop an understanding of how functional groups influence reactivity, why different halogens behave differently, and how experimental evidence is used to support chemical theory. Halogenoalkanes are defined as organic compounds in which one or more hydrogen atoms in an alkane have been replaced by a halogen atom, typically chlorine, bromine, or iodine. Throughout this topic, learners are expected to use appropriate chemical terminology, draw and interpret mechanisms using curly arrows, and apply their knowledge to unfamiliar exam questions. The structure of halogenoalkanes is based on the alkane framework, with a general formula CHX, where X represents a halogen atom such as fluorine, chlorine, bromine, or iodine. The carbon atom bonded to the halogen is sp³ hybridized, giving a tetrahedral shape with bond angles of approximately 109.5 degrees. Halogenoalkanes are classified as primary, secondary, or tertiary depending on how many alkyl groups are attached to the carbon bearing the halogen. In a primary halogenoalkane, the carbon bonded to the halogen is attached to only one other carbon, whereas in tertiary halogenoalkanes it is attached to three. This classification is crucial when predicting reaction mechanisms, particularly whether a reaction proceeds via SN1 or SN2. As the carbon chain length increases, boiling point rises due to stronger London dispersion forces resulting from a larger electron cloud and greater surface area. For halogenoalkanes with the same carbon chain length, boiling point increases down group 17, from chloroalkanes to iodoalkanes because larger halogen atoms have more electrons, leading to stronger instantaneous dipole-induced dipole attractions between molecules. More highly branched halogenoalkanes have lower boiling points than their straight-chain isomers because branching reduces surface contact between molecules. Halogenoalkanes are generally insoluble in water because they cannot form hydrogen bonds with water molecules, and the C-X bond is only slightly polar. However, they are soluble in organic solvents due to similar intermolecular forces. Halogens are more electronegative than carbon, so the C-X bond is polar, with a carbon atom carrying a partial positive charge and the halogen carrying a partial negative charge. This polarity makes the carbon atom susceptible to attack by nucleophiles, which are species that donate a lone pair of electrons. Reactivity trends among halogenoalkanes can be explained by considering bond enthalpy. The Ci bond is the weakest, followed by CBr and then CCl, meaning iodoalkanes react fastest in substitution reactions. Overview of nucleophilic substitution, SN2 mechanism, primary halogenoalkanes, SN1 mechanism, tertiary halogenoalkanes, comparing SN1 and SN2 mechanisms. Nucleophilic substitution is one of the most important reaction types involving halogenoalkanes. In these reactions, a nucleophile, such as the hydroxide ion, attacks the positively polarized carbon atom bonded to the halogen, resulting in the replacement of the halogen by the nucleophile. A common example is the hydrolysis of halogenoalkanes using aqueous sodium hydroxide to form alcohols. The general equation is Rx plus O ROH plus X. These reactions are typically carried out under reflux to ensure sufficient energy for bond breaking. The SN2 mechanism, or bimolecular nucleophilic substitution, is characteristic of primary halogenoalkanes and some secondary halogenoalkanes. In this mechanism, the nucleophile attacks the carbon atom from the side opposite the halogen, leading to the simultaneous formation of a new bond and breaking of the C-X bond. This occurs in a single step, meaning there is no intermediate species formed. The transition state involves partial bonding to both the nucleophile and the halogen. Because the reaction occurs in one step, the rate depends on the concentration of both the halogenoalkane and the nucleophile, which is why it is described as bimolecular. Steric hindrance plays a crucial role. Primary halogenoalkanes react more readily via SN2 because the carbon atom is more accessible to the nucleophile. The SN1 mechanism, or unimolecular nucleophilic substitution, is typically observed in tertiary halogenoalkanes. This mechanism proceeds in two distinct steps. In the first, slow step, the C-X bond breaks heterolytically to form a carbocation intermediate and a halide ion. This step is rate determining, meaning the overall rate of reaction depends only on the concentration of the halogenoalkane. In the second, faster step, The nucleophile attacks the positively charged carbocation to form the substitution product. Tertiary halogenoalkanes favor SN1 because the resulting carbocation is stabilized by 3 alkyl groups through inductive effects and hyperconjugation. SN1 reactions involve 2 steps and a carbocation intermediate, whereas SN2 reactions occur in a single step with no intermediate. The rate of an SN1 reaction depends only on the concentration of the halogenoalkane, while the rate of an SN2 reaction depends on both the halogenoalkane and the nucleophile. Structural factors are also critical. Tertiary halogenoalkanes favor SN1 due to carbocation stability, while primary halogenoalkanes favor SN2 because of reduced steric hindrance. Elimination reactions of halogenoalkanes, competing reactions, substitution versus elimination, hydrolysis, and the silver nitrate test, reaction rates and graphical evidence. In elimination, a molecule of hydrogen halide is removed to form an alkene. This reaction typically occurs when halogenoalkanes are heated with ethanolic potassium hydroxide. The hydroxide ion acts as a base rather than a nucleophile, removing a hydrogen atom from a carbon adjacent to the one bearing the halogen. As the hydrogen is removed, the electrons form a carbon-carbon double bond and the halide ion leaves. Aqueous hydroxide ions favor substitution, leading to alcohol formation, while ethanolic hydroxide ions and higher temperatures favor elimination, producing alkenes. The structure of the halogenoalkane is also important. Tertiary halogenoalkanes are more likely to undergo elimination due to steric hindrance, whereas primary halogenoalkanes favor substitution. The hydrolysis of halogenoalkanes provides experimental evidence for trends in reactivity. In this test, halogenoalkanes are warmed with aqueous ethanol and silver nitrate solution. As hydrolysis occurs, halide ions are released and react with silver ions to form silver halide precipitates. Silver chloride forms a white precipitate, silver bromide forms a cream precipitate, and silver iodide forms a yellow precipitate. The time taken for the precipitate to appear is used as a measure of reaction rate. Faster reactions indicate weaker C-X bonds, which explains why iodoalkanes react more quickly than bromoalkanes and chloroalkanes. Reaction rate data plays a crucial role in supporting theoretical explanations of halogenoalkane reactivity. In the context of hydrolysis reactions, graphs showing relative rates for chloro, bromo, and iodoalkanes clearly demonstrate the trend of increasing rate down the group. Halogenoalkanes in organic synthesis routes, assessment skills and data interpretation, required practical skills and good laboratory practice, summary and exam technique for halogenoalkanes. Halogenoalkanes play a central role in organic synthesis because they can be converted into a wide range of other functional groups. For example, an alkane can be converted into a halogenoalkane via free radical substitution, which can then undergo nucleophilic substitution to form an alcohol or elimination to form an alkene. Assessment of halogenoalkanes places strong emphasis on application, analysis, and evaluation. Students may be asked to interpret experimental data, such as reaction times or precipitate colors, and draw conclusions supported by chemical reasoning. Calculations may involve comparing relative rates or using given data to justify trends. Students must be able to follow written methods, control variables such as temperature, and record qualitative observations accurately. Risk assessment is particularly important when working with halogenoalkanes and organic solvents, many of which are volatile or harmful. Good laboratory practice includes using appropriate personal protective equipment, working in well-ventilated areas, and disposing of chemicals safely. Data processing skills, such as timing reactions and comparing results, are also essential. In summary, halogenoalkanes undergo nucleophilic substitution and elimination reactions. Their reactivity depends on bond strength, and they are valuable intermediates in organic chemistry. Make sure you can explain reaction conditions, products, and mechanisms for your A-levels exams. Thank you for watching.